All right, back again. Hello, ladies and gentlemen. I'm going to go ahead and talk to you about the different layers of the Earth and how they are somewhat similar to the Jupiterian Stripes in that they alternate direction. And ultimately, as they alternate direction, they get to the core, and the core is, in this instance, doing as we see it do on the surface of the Earth. It's rotating in a direction opposite the rotation of the planet. So the planetary rotation is prograde. The planet's core rotation, Earth, that is, the core rotation is retrograde. Okay. Yeah, I'm going to go over here. I had to make some corrections. I started a video and then I had to get rid of it because I had the arrows going the wrong way and they were all going the same way, and that was not my point. So as we begin to look at some of this stuff, I'm going to go to my picture down here. We're going to go right here. This particular view, as you see it, describes the Pacific striations as I first began to look at them. And like I was saying earlier, and I think I said before in another video, maybe when I deleted, well, actually I don't really delete them all. I just kind of like archive them because, those are the bloopers, right? Anyway, the point here is we have four extraordinarily clear striations that appear to be extremely close to parallel to each other. And I could line them up with different terrain features and different, very tall mountain peaks. And at first, my first impression was, because I'm still thinking plate tectonics, my first impression was that basically the Pacific Ocean was moving westward more quickly than the American continent, the North American continent. And as it was doing so, it was actually, in a sense, being extruded out from beneath the North American continent, in which case each of the striations were created by, say, for instance, anti-peaks, which are far greater in mass than the peaks above the surface of the Earth, and basically scoring what appeared to be a movement where everything was coming over. And I'm pointing to my computer screen, which you can't see, but follow my mouse. It's all going from the west coast right here and smack into Hawaii. And then I was like, well, maybe Hawaii originated over here and, blah, blah, blah. Well, the more I looked at it, the more I realized there's 1, 2, 3, 4, then there's this one, and there's this one. There's another one there, and there's another one. Well, what's the hell? What's going on around here? How many frickin' rocks are out there scoring the Earth, getting extruded out like Play-Doh? Something ain't right with the Play-Doh plan. So I had to take my Play-Doh toy and stuff it back in the closet and come up with a better idea. And that's when I decided I mapped them. And after I mapped them, I'm like, I need to count these because there's something parallel going on around here. So I counted all of them, and there were 9. And I'm like, that's funny. How many stripes are in Jupiter? Oh, look, and there were 9. I'm like, that's something that's oddly coincidental. And then I noticed that down around in a different part of the planet over here by South America were more parallel-like striations, and they weren't exactly in the same orientation as these striations. And then I'm like, what in the beaver stew is going on there? I mean, how many Jupiterian stripey-doo things we got going on around here? Well, long story short, folks, these stripes basically, if you draw them all out and map them, which I did in Google Earth, and somehow, don't ask me how, I was looking for them like crazy, pulling my hair out. Yeah, and guess what? I guess I deleted them. However, today I was able to find my PowerPoint, death by PowerPoint, right? I was able to find my PowerPoint of all of the work that I did. So I get to share that with you, and I'm very happy that I did save all that after all, because that took me hours, just mostly because I didn't know what I was doing when I did it. Today, if I was to do it, it'd probably take me maybe an hour. But then I was just like slowly, meticulously looking at every crevice on the planet. Okay, so anyway, this is our long story kind of short sort of thing here, right? Now, I was going to say that these lines are pretty much in, well, today's North Pole lines right up at the center, top dead center of these striations. And now, both sets of striations that I'm going to show you here shortly in this video were basically the last two major events on our planet. And the event that is responsible for creating these striations was the South China Sea impactor, which you can't see over here because it's back over here somewhere, right? Not necessarily right there, it's more like right out in here. And what you can see here is the other set of Jupiterian stripes that were more than likely scored by this impactor, the North Pacific Oceanic impactor right here. Now, I was speaking to a NASA scientist, and I told him, because I was talking to him on the phone, I had to get him oriented to where I was speaking of on the Earth. And to do that, I was telling him about the subterranean mountain ridge that what I call the Hawaiian subterranean mountain ridge, because Hawaii is the largest landmass in connection to that ridge. And I was telling him that it was in part, or at least part of, what I believe to be the North Pacific Oceanic impactor, which also was a world-class impactor in that it set the Earth into a state of worldwide liquefaction. The full extent of the damage it caused, not as easy to figure out as the South China Sea impactor, which was the most late impactor. And it's because a lot of whatever must have been or may have been in a certain arrangement at the time that one had occurred, it is erased. Some of it is erased. So in a lot of senses, the NASA scientists are correct. There are a lot of features on our planet that do get erased, but for the most part, there are so many impact sites out there, and we're overlooking them because we can't apparently we can't bring ourselves to believe that something so large really clobbered the Earth. And I'm here to tell you it did. It did, it will, and it's going to strike again. Well, maybe once every 1.1 billion years, but unless we know what the date was of each one of these impactors, which we might be able to get if we do some core samples in in the right areas. I'm telling you, right? You got to go to the right spot, right? So anywho, if you look over here follow my cursor, right there's a little speck of a dot. That's the pop. That is the point of penetration for that particular impactor. But this is all kind of stories. I mean, they do relate. It's a little bit off, but they do relate directly to the scores, because you see, these scores are created, I am theorizing that they're created by the forces given in the function of the asthenosphere, or the astheno streams that flow beneath the Earth, like the jet streams on Jupiter, but we don't have jet streams at the surface of our planet because we have a shell. So the jet streams are functioning beneath the shell. They could be lithospheric. I'm saying that they're asthenospheric, and I'm saying that the asthenosphere is the most viscous sphere within our planet, and it gets a little more sluggish as you get to the lithosphere, and there's probably a lot, who knows how thick these spheres really are, right? The diagram I'm going to show you makes the spheres look like they're way too thick to be what I'm suggesting. But if you want people to understand what it is that I'm describing in that particular diagram, then they have to be large enough to be able to see and notice a distinct difference between the layers in that sense, right? So I'm suggesting that the lithosphere is too tied up and too much involved in moving around the planet's inner topography, like anti-mountains, anti-valleys, anti-draws, anti-spurs, all of those masses underneath of our crust, underneath of what we can see. They have an effect. They have the same effect on the lithosphere as the surface of our planet has on water. So, that's the kind of things that are going on there. So we're thinking that maybe when I say we, I'm talking about, me. I'm thinking that that's pretty much the lithosphere is tied up with all kinds of googly-gog. So now that leaves us the asthenosphere, which has the most fluid motion available to it. Now, I'm going to go to my other picture. Actually, I just have to go boop. Oh, there it is. Now, I did this a while ago. I made this picture. Okay, so these stripes that I have showing here from Google Earth, these stripes are the second set of stripes, or the older ones, which were affected by the impact of this little guy right here where my cursor is, the North Pacific Oceanic Impactor. Now, if you can't see it here too well, right? But if you take that impactor, like I said in one of my videos, and you compare it to the South China Sea impactor, hey, this bugger was huge. I do mean huge, way bigger than this one. But this one's more recent because the waves have overswept the damage that this guy caused. So this is newer, right? It's still just as devastating. I mean, look at all this crazy stuff that guy started. Yeah. All right, so you have the Jupiterian stripes, and the primary stripe is always the equator. There will always be an odd number of stripes because the very equatorial stripe in and of itself is always going to be going in the same direction as the planetary rotation, always. And then that means that all other paired stripes are going to be going in alternating directions from the equator, as you see here. And this one is to describe the strength of force. So the greatest strength of force is number 1, followed by number 2. And you'll notice that the even numbers are in the southern hemisphere, while the odd numbers are in the northern hemisphere, because the strength of the southern hemisphere jet streams or asthenospheres are stronger because the South Pole is the base of the planet, and there's a lot greater force striking the planet from this side, being the galactic gravity, okay, the galactic gravitational force. So this is how you look at it. Now 11 and 10 are actually not, they are not, and I titled it lithostreams because this was before I really got to the point where I had to boil it down to asthenospheres to my understanding, right? Now, streams 11 and 10, those are actually polar ring areas. They're not separate streams. They actually consist of 9 rings in themselves. So you end up with a total of 27 Jupiterian stripes and rings, okay? And that's how gyroscopic properties of DRCBs works. DRCBs, all differential rotating celestial bodies. I'll go ahead and say it again. All differential rotating celestial bodies includes, I'm going to go back on this one thing. I contradict myself because I was into the superlative of all, and I included round balls in space in their entirety. And I apologize because that isn't what I meant to say. All DRCBs, meaning all differential rotating celestial bodies, have these properties. RCBs don't. An RCB, that's right, Doodle. An RCB is a rotating celestial body. Rotating celestial bodies refer to comets, if it's rotating, but in most cases, like some of the asteroids we see, like the flying Volkswagen asteroids, where they're not really round, but they're rotating, they're like cigars or broken shards from whatever the heck blew up, and they're going through sky like this, turning over and over and over again. It's rotating. It's a rotating celestial body, but it does not have the property to give it differential rotation. And, however, I know, I said and however together. Yeah, I know. Well, anyway, this is how it works, right? Gravity, in its simplest term, is the vacuum of space. Okay, and then the other part of that is the cosmological common denominator is the vortex. So without the vortex to create the vacuum, you will not have gravity. Okay, now when you start adding a whole bunch of differential stuff in there, your gravity gets stronger. Okay, because you just got a whole bunch of crazy vertical forces going on, right? However, if you have just that flying Volkswagen flipping through the sky like that, it doesn't have differential rotation, but it does have a rotation, and that rotation creates a vacuum. That rotation is rotating on a vortex. You have that the axial tilt of that particular object has a vortex that it's at its center, right? And it's rotating around that vortex, and as it does, you might just say that this bulbous end and this bulbous end of that particular rock, as they're going through, one, they're creating pressure on the side that's moving forward, and they're creating a vacuum or a very low pressure which sucks everything in toward its core down here, and it's the same thing. And it has, in this essence, it has gravity, but it's a very weak gravity, not nearly as strong as what you get with a sphere. Okay, now DRCBs includes stars, terrestrial planets like our Earth, black holes, or what I refer to as terrestrial stellar objects. The reason I refer to them as terrestrial stellar objects is because some scientists proposed that there are white holes. Well, of course there's white holes, but it's still not white. I don't care how white you think a white hole is, it ain't going to be white. It's going to be black. Why? Because the stellar mass surrounding it is always going to be brighter than its own luminosity, no matter how much of that stellar mass it eats. And the luminosity of the black hole depends on the rate of stellar feed. So the higher the rate of stellar feed, the brighter the black hole. However, it's still not going to be brighter than the stellar mass, so it's still a black hole. But either way, the term terrestrial stellar object covers all black holes, regardless of their level of luminosity. And so, on top of that, some people might be confused. Well, how do you get terrestrial with stellar? Well, fine. A black hole is an extraordinarily large planet. That's all it is. Just great big. It's a great big planet Earth. The only problem is it's so big, it's sucking in all the stars, and all the stars are splattering on it like bugs on a windshield. And what happens when the bug hits your windshield? Right up your windshield, and you got this crap all over your windshield. Well, that's what happens on the black hole. You go, there goes another star, there goes another star. Well, all that plasma from those stars, it just doesn't dissipate. It went into nowhere. It's a magic trick from hell. Well, it just went bloop, and it was gone. No, it wasn't gone. It didn't get sucked into the darkness of who knows where. It hit the planet. It splattered its guts on the planet, and now the planet's surface is covered with plasma from stellar objects. So it becomes a terrestrial, because it's terrestrial first, like the ingredients that you get inside of a package at the store. What's the first ingredient? The first ingredient is the ingredient that you see the most of inside the package, in which most cases it's almost always sugar, right? So the sugar is like the primary ingredient that makes everything we eat, because we're all a bunch of sugar-eating dog hair. Okay, anyway, you get the idea, right? So it's terrestrial stellar object. Now that I went into all this detail for that, but it's the same thing. It's a DRCB, just the same as any other DRCB in the universe. Okay, so now what's the other one? Gas giants. Okay, there was only one left. So you have stars, you have gas giants, you have TSOs, and you have terrestrial planets. Ta-da-da! And they're all DRCBs. Well, maybe not all the terrestrial planets are DRCBs, because, like, well, we're not so sure about Mars now, are we? I don't know if that one's doing any kind of crazy stuff. Looks like it pretty much spewed all of its inner guts out there through Olympus Mons, right? Anyway, we're going to go on to our other stuff. I'm going to go to the next thing here. Whoop. Oh, now this is the one where I screwed up the arrows. These two arrows are going the same blessed way as all the other arrows. Now, I'm sorry that this diagram is so complicated. I wanted to make sure I got it all in there. Pretty though, if you think about it. It's all kind of like, looks like one of those things you would do with those wheels back when I was a kid, like in the 70s, and you did take this pin, you whiz it around, and it makes this cool design. Yeah, it's kind of looking like that. Well, anyway, I can't forget what it was called. Anyhow, the black arrows represent the direction of flow because the equatorial vortices, as described here, the brown lines going in, funneling in toward the core, they're anticyclonic. That's why it says anticyclonic equatorial vortices. Over here, 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 and here, because there's 4 of them. Oh, hey, is that a corner? Ooh, there's a corner. Oh, there's another corner. Oh my God, that's 4 corners. I wonder if that's 4 corners of the earth. Wouldn't it be weird if all of those folks in the Bible that wrote the Bible knew more than we do? Because they're always talking about people getting spread out to the 4 corners of the earth when you're in trouble. And, well, here's the 4 corners of the earth here, so it's kind of like, wow, that's sort of strange right there. I wonder if that's got anything to do with what they're talking about. I don't know. So anyway, things that make you go, All right, here's my brown crust. Brown crust is rotating in this direction, which, as we look at it here, it's going clockwise. Now, the planetary rotation, which is not described on this particular diagram, is naturally going counterclockwise. So as the planet is rotating this direction, the crust is rotating this direction. And it's not really rotating in a direction, it's being forced in that direction because of the coefficient of solar wind pressure drag, which is described in one of my diagrams somewhere. Okay, so anyway, it's going westward. It's going westward. Did I say westward? It's going clockwise, and then you alternate, and the rotation of the lithosphere in this zone is going in the opposite direction, which is going counterclockwise. And then you have the rotation of the asthenosphere here going clockwise once again, and then the mantle over here, you got the arrow, it's going counterclockwise, and then you have the core of the planet going clockwise in the exact opposite direction as the planetary rotation, right? Isn't it interesting how these all seem to be alternating? And Antarctica is our greatest proof of the core of the planet rotating in the opposite direction. Just need to get people to focus on it and actually open up their minds and see what I'm talking about is inarguably a fact. Okay. Now, that pretty much just narrowed this one down. All right, so we're going to go over here to this guy. And this is my first one here, you see. I even named these. I don't even remember doing that. So I named them. So I had to change the name because I was calling this the Chinook lithostream. And of course, like I said, lithostreams, I should be going back and renaming it. But then I have to resize all the boxes. It just seemed like a pain in my butt, so I didn't do that. I just really wanted to get this out there. So it's not. It might be a lithostream, but I'm sticking to asthenostreams for right now, okay? So up here you have the Chinook polar rings, because there's what? There's 9 polar rings, right? And then you have the Antarctic polar rings down here in zone 11. And these are not numbered in zones of strength. They're numbered in numerical order from top to bottom. Okay, so the Antarctic polar rings, which are another set of 9, because we are currently living in the Jupiterian 9-stripe period. That means that the last 2 massive impactors from outer space clobbered us recently, geologically speaking. Okay, naturally, it wasn't 65 million years ago, right? That's not what we're talking. Chicxulub probably takes the bite on that one, right? But these guys definitely, the last, well, who knows how long the Earth has actually been in the Jupiterian 9-stripe rotational speed. When I go back to Pangaea and I map out the theoretical stripes from Pangaea, I end up with, guess what? 13 stripes. So if Pangaea, as it might have been collectively in the beginning, got struck and was hit by a world-class impactor, and that impactor caused scores to develop from the asthenosphere through the crust, and it turned out to be 13, then that means that at the time that impactor struck to the last time that the South China Sea impactor struck, the Earth has decelerated by 2 sets of Jupiterian rings, or Jupiterian stripes. So I say 2 sets because you went from 13 to 11, and like I said earlier, it's always going to be an odd number. And maybe not necessarily a prime number, but definitely an odd number. And so you're going from 13 to 11 to 9, so we lost 2 sets. If you lose a ring in the north, generally you lose a ring, or if you lose a stripe in the north, generally you lose a stripe in the south. Not necessarily always the case. There's a unique case where Jupiter lost 1 stripe in the southern hemisphere. So what does that tell us? It tells us that because Jupiter is a gas giant, it has that dynamic where the southern hemisphere rotational speed could be decelerated while the northern hemisphere is unbothered. And the suggestion there is a whole different ballgame. It actually boils down to an extragalactic gamma ray burst. Gamma ray bursts, they have their own, generate their own gravitational force. And I can explain that now, but I'm not going to because that's a whole different story. But anyway, that's the only way you're going to get the southern hemisphere to be rotating at a slower rate than the northern hemisphere. So if it had been a planetary effect, then Jupiter would have actually lost 2 Jupiterian stripes, reducing it from 9 Jupiterian stripes to 7 Jupiterian stripes. Now, I guarantee Earth's rotation, to some extent, may or may not have been decelerated because maybe the gravitational force of the GRB wasn't strong enough to affect terrestrial planets, but most definitely strong enough to 1, affect the sun, and 2, affect gas giants. All right? And even then, it wasn't even strong enough to affect the entire planet. It was only strong enough to affect the southern hemisphere because the GRB basically, here's our solar system at some angle like this, the GRB off in some distance down here from the Indus constellation, not necessarily from the Indus constellation, but from the origin or from the direction of the Indus constellation came past us this way here, piercing through our galaxy at the same time that it went past our solar system. And it could be that that particular GRB originated from a location far beyond the Indus constellation. The only thing is, we can only see as far as the Indus constellation right now. So we can't really see where it came from, necessarily, right? Yeah, that's the whole idea, right? So, that also affects the Earth. That also affects Jupiterian stripes when they are being scored, or when they're on a gas giant and not being scored. Because the Sun and the Jupiter, they don't score anything. It's gas. It's all... Yeah, all the little doodly-doodies. All right. So I have names here. I'm sure with all my babbling on, you guys have probably read each name by now. I gave them all names, so there you go. Here's your central one. And then it goes bloop, 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 back and forth all the way up. Now, if I go down here farther, we're going to go down all the way down to this guy here. Boop. And here's the one that was actually preceded the... you notice here's the primary stripes that we see today. These stripes preceded the current stripes, and the North Pole from here is actually a few degrees off from where the North Pole is today. So we're still in the Jupiterian 9-stripe period. The North Pole is still where it is, where it was when, which means we pretty much had a steady, well, what would seem to be a steady axis, right, or axial tilt. And I can tell you this, that the Earth's axial tilt is constantly migrating. That's how you get the helical path going down through here in the Pacific Ocean. It's continually migrating. So it just might have been migrating for 1.1 billion years or longer. Who knows when the South China Sea impactor hit the Earth. So and then before that, right, you still have the 9-stripe period, just the axial tilt of the Earth was in a different location, that's all. So that's how that material works, and I think that was, oops, my bad. That's it for this video, folks. That pretty much explains the Jupiterian Stripes. So, yep, that's about it right there. Okay, I'm going to go ahead and close this one out. I got a few others to do. Got some things I want to do today to talk about everything I can cover as much as possible. It was nice talking to you guys, and I'm going to let you go. Bye.